Alright, hello, and welcome to part 2. Let's get on. Alright, so question 16 is an experiment question. Kim and Ali perform an experiment. Alright, there's the method, and these are the results that they got. So Kim used the data in the table to obtain the mean value, so this should be screaming some sirens at you, and her result was G is equal to 9.3, which is quite different to 9.8. Ali used the results to produce the following graph. Ali's line of best fit was used to calculate G. This is usually the way to go with all experiments. Outline 2 changes that could be made to the experimental procedure that would improve its accuracy. So let's see. So this point screams out to me. Release the mass and measure the time for one period, where if you did this experiment in school, you would have probably measured the time for 10 periods, and then divide that result by 10 just to get you one period. This is so that you limit your reaction speed time. So that's one. And let's see. They just want to improve accuracy. They used different lengths, which is okay. My suggestion would be use longer lengths than 0.08, because remember, this is not a point mass. And the longer you have it, the smaller the radius to length ratio of this would be, and you won't get so much of a well, you get this more acting as a point mass the longer L is. So this here is only 8 centimeters, which is really short. So that's what I would write. Compare Kim's and Ali's method. Alright, compare straight away. Table. Draw a table, and then you get 1 mark just to identify that Ali method is better. So Kim's is the mean result, and Ali's is the line of best fit. Calculate the value of G. So you want to pick points that lie on the line, so you can even pick 0, 0. That looks like it lies on the line. And you can just pick this 0.08 point. Get the gradient. The gradient is equal to 4 pi squared over G, and you can use that to solve for G. Alright, describe 2 difficulties associated with effective and reliable communications between satellites and Earth. Alright, we can probably just start off with defining what a satellite is. So a satellite is a man-made object that orbits Earth. Low LEOs, or so low Earth orbiting satellites, orbit like, I don't know, 12 times in one day. So we don't have a clear line of sight with them. And what else can we have? They really high satellites aren't protected by the Earth's magnetic field. So they just want 2 difficulties and just relate them back to effective and reliable communications. I'm sure, and it's a describe, so it's not that big. Okay, the graph shows the percentage transmission of electromagnetic radiation of various lengths through the Earth's atmosphere. So we see that high, very short wavelengths, so this is probably in the gamma radiation, they're all blocked. And we've seen the low wavelengths, they can go through our atmosphere. So they give us a frequency. We know F equals V equals F lambda. We can solve for lambda, find out what wavelength it is, draw it on the graph, and it will most probably be at a point where the percentage transmission through atmosphere is 100%, and that's why we are using this particular frequency. Anyway, in one of Einstein's famous thought experiments, a passenger travels on a train that passes through the station at 60% the speed of light. According to the passenger, the length of the train is 22 meters from front to rear. Okay, a light in the train carriage is switched on. Compare the velocity of light as seen by the passenger. So this is a compare, but we can easily just write this as one sentence. The velocity of light is the same in both frames of reference. Calculate the length. Okay, I can try to do this. So I'm going to calculate the 1 over the square root first. So 60 squared is okay. I'm going to do 0.6. Nope. 0.6 squared. Alright. 1 minus 0.36. And then take the square root 0.8. And we're going to times this by 22. So the length is 17.6 meters. Make sure to show the equation first. So go to the data sheet, find your equation, and just write it. You get 1 mark straight away, just for identifying the right equation. Substitute correctly in, and then solve correctly for t. That'll be your 3 marks right there. Alright, question 20. A student is investigating inertial and non-inertial frames of reference. Each activity and the student's observation results are recorded in the table. Justify the student's conclusion that the boat can be regarded as an inertial frame of reference. So straight away when I look at this, I think the boat is an inertial frame of reference. Because the boat is floating on a large calm lake, it remains level during these activities. Alright, so I'm going to leave this one last, but I'm going to go through this one first. So a ball is rolled from one side to another. The ball rolls across with constant velocity, so meaning it's not accelerating, and so it's an inertial frame of reference. Same reason here, not accelerating, inertial frame of reference. So when the ball is dropped from a set height, it's accelerating downwards. And this is because the ball is not in the same reference as the boat. Once it hits the boat and stays on the boat, it won't accelerate on the floor of the boat. So we need to justify that this is not in the same reference as the boat. 3 marks, and then justify, we say, oh, it's correct. Okay, in this science fiction novel, alright, yeah. Okay, so to reach the moon, the capsule must leave the cannon at a speed of that number, which is very large. The cannon must have a length of 215 meters, over which the capsule can be assumed to accelerate constantly. Calculate the magnitude of the acceleration required to achieve this speed using the cannon. Alright, we can calculate average acceleration and get the time to figure out how long it stays in the barrel of the cannon. And then we know final minus initial, and we can just divide that by time to get acceleration. So the average, the initial velocity here is 0, so the average acceleration would be just half of this, right? And then we can do distance divided by the average acceleration will give us time. And then we're going to do final velocity divided by time will give us acceleration. And that would be, just by looking at these numbers, acceleration is going to be extremely large. Now, again, just by looking at this question, explain why Julie's method is unsuitable for sending a living person to the moon. The verb here is explain. So remember, we want to identify what the g-force is, and we have that because we have the acceleration. describe it's really high and then explain. So remember that explain means cause effect. So it doesn't matter which way the person's going to be orientated, is going to experience a redout or blackout, because just acceleration is going to be so high, and he will literally be crushed. So you won't be sending a living person to the moon. Alright, question 22. Two types of generators are shown in the diagram. What is the function of the brush in a generator? The function of a brush in a generator is to maintain electrical conduct to the generator and the load. 1 mark. Which of these generators is a DC? Generator Q. That says justify. Alright. So generator Q reverses polarity twice every revolution, while generator P doesn't reverse at all. So when the axis flips around, back EMF is going to be, I should say, just the voltage produced will be negative, and since this flip doesn't flip it around, it's going to change direction, meaning that generator P is alternating, and we can argue that generator Q will flip around. So even though it's like a bumpy curve, it's still in one direction. So that's direct current. Alright. Outline why AC generators are used in large-scale power production. So this question is basically saying, why is AC generators better than DC generators? Well, we can see that they don't have these cuts, so they last much longer. And it's 2 marks, so we probably want 2 reasons to be very safe. And also AC generators, we can use transformers, whereas direct current we can't transform. Alright, question 23, state Lenz's law. So Lenz's law is basically back EMF. Whenever back EMF is produced, it's in the opposite direction of what caused it. So this is just a conservation of energy sort of thing. Okay. When the metal rod is moved upwards through the magnetic field as shown in the diagram, an EMF is induced between the 2 ends. Which end of the rod is negative? Alright. So our fingers point from left to right. Our palm is pointing down because the direction of motion is up, and our thumb points to end X. So I'll probably say end X, but then again, conventional current, yeah, it's all a mystery, but I would apply the left hand rule. Explain how. So you have your verb, and then you have your verb modifier. Explain how the EMF is produced in the rod. So basically, there's lines of flux between these 2 magnets, and this rod is a current-carrying conductor in which it's cutting lines of flux. So basically, produce an EMF. I don't think that's enough for 3 marks. Anyway, moving on. Explain how the principle of induction can be used to heat a conductor. Alright, so induction is the process. Well, we probably should start off with identifying what induction is in the first place. So just start with induction is blank, fill it in. And then I would go on to how it produces heat. So basically electrons collide with the vibrating lattice, or have violent collisions, which causes the lattice to vibrate more, and thus generating heat in the conductor. It's explained how, so it's a big verb, but it's only 2 marks. Alright, this question. In terms of band structures and relative electrical resistance, describe the differences between a conductor, an insulator, and a semiconductor. Alright, straight away. well, if you want, you can define each of these, but it's describe and goes describe the differences. I would just draw a huge table straight away. All right, let's do this. And diagrams, of course. So here's our insulator, semiconductor, and conductor. Alright, so I'll leave one box to draw the diagrams on how insulator, so they have a large energy gap. Semiconductors is like together, and conductors is they basically overlap. Yeah, horribly drawn. Alright, then we go to free electrons and how many free electrons they have. So insulators basically have no free electrons. Semiconductors have few and conductors have a lot. Then we go into resistance, ohms, and then we can go into conductance. So just draw a nice huge table and don't leave any parts of the table blank, because then that shows that you don't have any information on that part. But I would draw a really big table and just put descriptions about conductor, insulator, semiconductor, so when the marker marks it, he can clearly see the differences between these three. And remember, we got to relate it back to band structures and relative electrical resistance. Okay. Question 25. A pair of parallel metal plates placed in a vacuum are separated by a distance of this and have a potential difference of that. So this is straight up an application of E equals V over D. That's in the formula sheet, so you can do that quite easily. Now this is F is equal to QV, so Q is the charge. Remember that a charge is negative. Alright. Now, a beam of electrons is fired with a velocity of really big between the two plates as shown. Magnetic field is applied between the plates, sufficient enough to okay. So is these the same plates? Yeah, I think they are. So we know the force. Calculate the magnitude and direction of the magnetic field required between the plates to stop the deflection of the electron beam. Alright, so this field is going down the plate, so meaning that the electron will be deflected up. We can apply our left-hand rule, and the magnetic field needs to be acting into the page. Alright, so we got the direction part down. Now magnitude, there's a formula in the data sheet that you can use to solve this. You have the charge, you have the speed, you can calculate the magnetic field. Some materials, alright, question 26. Some materials become superconductors when cooled to extremely low temperatures. Identify 3 properties of superconductors. So, one property that's really obvious is that they have 0 electrical resistance. So electrons just pass freely without losing any energy. Another property, and then we can go back to the negative side effects, is that they're brittle. So meaning they are very cold, so they would be quite brittle. Some materials would be. And one more, they can generate super magnetic fields. Damn it. Well, I'm sure you can do this part. It's an identify verb. Should be fairly simple. There are 2 areas in which energy savings can be made by the use of superconductors. These are electrical generation and transmission, transportation, and then discuss how energy savings can be achieved in each of these 2 areas. So, discuss. Okay. So discuss is positive and negative effects. So again, I would draw a table. My table would be a little bit different. So here we go here we go here, and here we go here. So we can have positive here, or positive things, negative things here, transportation and electrical transmission. Just write what you know here. So transportation, maglev trains, very fast, and then negative things for both things are like superconductors are hard to maintain, they have to be very cold, some are unstable in certain environments, things like that. And we have four datas, 4 marks, should be fairly easy. Okay, and that is it. I hope I've explained each question well. Yeah, thank you for watching.